Now we're going to talk about some laws. Laws tell us what happens, not explaining why. And the history of the gas laws is pretty interesting, but we're just going to get a little tiny taste of it. Boyle studied the relationship between pressure and volume of a gas. He found that the pressure of the gas sample depends on its volume, and vice versa. So if the temperature of the gas is present and the amount of gas is present, then the pressure increases if there's a decrease in volume, and it decreases if there's an increase in volume. And what we say is that it's inversely proportional. So the pressure is proportional to 1 over the volume. If the volume gets big, the pressure gets small. If the volume is small, the pressure is large. And if you think about a balloon, if you squeeze that balloon and make it smaller, what's going to happen to the pressure? It's going to be greater, right? Because you're squeezing that gas into a smaller container. Let's look at a bicycle pump. When you pull the handle on a bike pump up, the volume in this cylinder increases. So here we see there's a piston in here. It's the same idea as a syringe. And so you've got this piston that seals. When you pull it up, it increases the volume inside. So going from here to here, the volume gets larger. That causes the pressure to decrease. Down at the bottom, there's a one-way valve on the bike pump. And when that breaks, your pump doesn't work anymore. So this allows air to come in, but not out. So you lift up on the plunger, and the gas comes in. And then when you press down, you're making the volume smaller, you're making the pressure higher. And that forces air into the bike tire. Forces air into the bike tire. And so you can take air that is not pressurized and you can impose pressure on it and cause it to go into your bike tire and inflate the tire. So Robert Boyle was the one who studied the relationship between pressure and volume, and this was back in the 1600s, so this was a long time ago. And in his experiments, he did them with a constant temperature and a constant number of gas particles. Because it turns out the temperature of the gas and the number of gas particles also affect the pressure and the volume. And it's hard to look at more than 2 variables at once. So what he did is he changed the pressure and looked at the volume, or changed the volume and looked at the pressure. And this is one way to state Boyle's law. The volume of a gas and its pressure are inversely proportional. And that alpha means proportional to. That means if this side goes up, the other side goes up. So this is how he did his experiments. This was called a J tube because it's shaped like the letter J, right? So this side is sealed, and there's some gas in there, and then he's got mercury, and the other side is open to the atmosphere. Now, if both sides were open to the atmosphere, just like water, we would expect the mercury to be level on each side, right? Why is the mercury pushed down on this side and up on that side? Because there's pressure in here. The pressure over on this side is greater than the pressure on the other side. And the difference in pressure can be measured by the difference in the heights of the column of mercury. Mercury is a very cool element. It's a metal, and it's very dense, but it's a liquid at room temperature. Sadly, it's also toxic, and so we can't play with it. Bummer. If he added more mercury, then this side of the mercury would go up because it's squishing the gas volume. It's squeezing it, it's compressing it. But now the difference between the mercury on this side and that side is greater, which tells us the pressure difference is larger. And so these are very low-tech experiments. They didn't have any technology back in the 1600s, right? They didn't have electricity. So they did these amazing things with no technology. So you add mercury, you measure the height here, which tells you the difference in pressure between inside and outside, and they could measure the volume of the gas as it got smaller and smaller. And then they would graph it like this. And so here's the pressure. As the pressure increases, the volume goes down. And that's what Boyle's law tells us. The kinetic molecular theory explains these observations. So here we have a cylinder with a movable lid, and this is a weight sitting on the top. So here we have a volume equal to 1 liter, and the pressure here is 1 atmosphere. We're not adding gas to this, we're not taking gas out. All we're doing is increasing the size of the weight on the lid. That causes the lid to go down. Now the volume is half as large. The volume has been cut in half, it's 0.5 liters. The pressure gauge tells us that the pressure doubled. So you cut the volume in half, the pressure doubles. If you cut the volume to 1/4, the pressure quadruples. It's a proportional relationship. The pressure is higher here because there are more gas collisions with the walls of the container. Because the container is so much smaller, they're going to run into the walls more frequently. Right? If you took, what would be, there's all these benches in here, but you take this room and you have people walk around blindfolded just until they bump into something. And then you take the same number of people and you cut the room in half. Are people going to run into stuff more often? Yeah, because there's less space. So when the particles are closer together, they run into each other more frequently. So this is the most useful expression of Boyle's law. P1V1 equals P2V2. And we're going to do a lot of gas law problems. We can answer questions like this. A cylinder equipped with a movable piston has an applied pressure of 3.0 atmospheres and a volume of 5.0 liters. What is the pressure of the cylinder if the volume is decreased to 2.0 liters? So here we are again with the word problems, right? I don't hear any cheering. That's okay. Oh, I did something. Here, I'll just do that again then. So the numbers are going to be important, and the units are important. So I'm just circling the numbers and their units, because the unit tells us what this is measuring. Liter is a volume unit. Now it says the volume is decreased, but sometimes it doesn't tell you it's a volume, but you can know that it's a volume by looking at the unit. 5 liters, there's another volume, and atmosphere is pressure. So the best approach to these problems is to make a table to organize the information. So we're going to have condition 1 and condition 2. We don't need to care whether it's the initial and the final. It's just two different sets of conditions. Because things are changing, right? You've got a movable piston. The pressure is this and the volume is that. Those two numbers go together. And so we'll just call that condition 1. So I'm going to write these numbers in as I come across them in the problem. So 3.0 atmospheres. And that is a pressure. So I'm going to label this column pressure, P for pressure. 3 atmospheres and 5.0 liters, those two go together. Liter is volume. So that's the volume column. Now they're saying, what is the pressure? That's the question. If the volume is decreased to 2 liters. So I'm going to write 2 liters over here. because this is what we're starting with, and this is what we're ending up with. The volume is 2 liters. We don't know what the pressure is. That's what we're trying to find out. You still with me? Yes? Oh. Let me see if I can fix that. It's a dumb screen. There, is that better? So 1 and 2. So any questions about how I put the numbers in the table? So we're going to use these labels. P in the first row, this is P1, this is P2. So instead of the question mark there, I'm going to give it this identity of P2. So that's P2. This is V1 and V2. So these are the 4 things we need for this equation. We've got 2 pressures, P1 and P2. We have V1 and V2. We're going to use this equation, and we need to rearrange it. P1 V1 equals P2 V2. What are we looking for? We're looking for V2. So, no, P2, sorry. So I'm going to make P2 yellow. We need to rearrange this equation and get P2 by itself. Sometimes students want to put the numbers in first and then rearrange it. I do not recommend that. Lots of crazy things happen. So rearrange it first and then stick the numbers in. So the idea with rearranging equations is we need to be fair. P1V1 equals P2V2. If we do something to one side of the equation, we have to do exactly the same thing to the other side of the equation so that it is still equal. It's like a teeter-totter. If it's perfectly balanced and you put a box on one side, you have to put a box on the other side to keep it balanced. We want P2 by itself. We have P2 multiplied by V2. To get rid of V2, we're going to do the opposite. So I'm going to divide by V2. Because what is V2 divided by V2? It's 1. Anything divided by itself is 1. P2 times 1 is just P2. And so then if I did it to one side, I have to do it to the other side. Now I'm just going to rewrite that. Sometimes it gets a little messy. This one didn't get too messy, but sometimes it gets a little messy. So just copy it over again. That's the equation we're going to use. Be careful with the 1s and 2s. Okay? It's very easy to switch them around. So just be aware of that. Now I'm going to, for P1, I'm going to substitute what P1 is. It's 3.0 atmospheres. Write the unit in there. It's part of the number. So it's P1 times V1. V1 is 5.0 liters. And that's divided by V2, which is 2.0 liters. And then look at the units. Liter over liter cancels out. I'm left with units of atmosphere. This is a good sign. If your units don't work out, you messed something up. There's so many ways to mess these up. Now I just use my calculator, which, I really wouldn't have to, but I'm going to anyway. 3 times 5 divided by 2, 7.5. So pressure 2 is equal to 7.5. How many sig figs should that have? 2. All my other numbers had 2. So 7.5, and the unit is atmospheres. So if I take the volume from 5 liters and compress it to 2 liters, the pressure is going to go from 3 atmospheres to 7.5 atmospheres. Any questions?